Hello and welcome to Module 1 of DC Analysis. In this module, we're going to go through several learning goals. We're going to review the SI system of units, understand the prefixes that we're going to be using throughout the course. Then we're going to talk about the basic definitions and of the basic electrical quantities such as voltage, current, and power. And we're going to look at the symbols that we use for those definitions, as well as the symbols that we use and the definitions of independent and dependent sources for those quantities, such as current and voltage. We're also going to define power, how we define power in terms of the energy that we supply or absorb from systems and circuits, and we're going to be able to calculate the power absorbed as a negative quantity by a part of a system or a circuit element, or we're going to be able to calculate the power as a positive quantity as it is sourced by an element or a part of a circuit. And that's what we use, what we call the passive sign convention. So again, let's look at the standard prefixes, and we can see that here we go from the smallest prefixes, 10 to the minus 12, we call that pico. If it's 10 to the minus 9, we call that nano. 10 to the minus 6, micro, and 10 to the minus 3, milli. So that's in the the fractional part of the scale. Then beyond that, if we have 10 to the third, we call that a kilo. If we have 10 to the 6, we call that a mega. And if we have 10 to the 9, we call that a giga, and a 10 to the 12 tera. There are others beyond 10 to the 12 and also smaller than 10 to the minus 12. But these are the main ones that we're going to be talking about in this course. So let's look now at the one of the basic quantities of electronics and electricity, the current. So if we imagine that we're looking at a conductor is just simply a piece of material that conducts electricity, and if we could look at a specific point along that conductor and watch the amount of charge as defined by a fixed number of electrons that are moving from atom to atom and jumping and moving through that point in the conductor. So we would call that a unit of charge. And if we look at that point and we look at the rate at which that charge is moving through the conductor, we will have what we call a current. So current would be the rate of change of the charge that is moving along a conductor per unit time. Now, if we wanted to know how much charge went through that point along the conductor since some point in time, we could integrate the current. So we could integrate the current here, and we could integrate that from the time that we are interested in this case, let's say forever, until the point that we want to measure that current with an integration variable of x. And if we integrate the current, we will have the total amount of charge that went through that conductor if we had some function for the current. Now we have two types of currents. We can have constant current that doesn't change through time, and we call that DC, or constant current. Or we can have a current that is some function of time and it changes as time goes by, and we call that AC or alternate current. Let's take a look to get an idea of the dimensions of current that we find in nature. For example, if we were to measure the synaptic current that is firing between neurons in the brain, we would see that that's in the order of picoamps. If we look at the currents that are present and integrate the circuits, the ones that would be in your cell phones, in the memories that are in your computer, we would see that those are well below the microamp level, and that's why we can get electronics that function for such a long time on very little or small batteries. Um, Now, once the current gets into the milliamp range, you start feeling it, and it is current that is harmful, because it is the one that when it gets in the tens of milliamps, it can cause that ventricular fibrillation in humans that can actually distort or stop the beating of your heart. Now, when we get up to household appliances, we can see that we are in the single digit amps. This is a very dangerous current levels. And if you are in industry, in a factory, and you have a larger motor, those would be AC, but we will have hundreds of amps. Now, the actual current that can be delivered by a lightning bolt is in the thousands of amps. And, of course, that's very, very dangerous, as we all know. Now, another quantity of interest in electronics and electricity is the voltage. If we are going to have a current that is going to carry information or some signal in a circuit, that current has to be that charge that charge movement that defines the current has to be pushed, has to be moved. That action has to be precipitated by something, by some external force, and that pressure we call voltage. So it's the force that makes those charges move and produce a current. So we call that the amount of work or energy that we have to put in a system per unit charge to move that charge to cause a current is a voltage. That's how much difference in work or energy has to be there per unit charge to move it to produce a current. So, for example, if I have some circuit here, okay, I apply some source of 2 volts with a positive sign here. I define that by convention. So I'm going to have 2 volts applied here, and depending on the load of this circuit, that's going to demand that I have that if I put 2 volts, depending on the load here, that's going to cause some current to come into that circuit. Okay. Now I can reverse the sign and say that, or rather not reverse the sign, but I can put a voltage source, another voltage source that is negative, and I'm going to have another current. Now, by convention, we say that the current flows, as I drew here, from the positive terminal of this voltage source and returns to the negative terminal for a positive voltage, here. Okay. So if I have a voltage source that is negative, and in this case minus 5 volts, what that really means is that with the same sign convention that I have here, is that the current is actually flowing from the negative terminal, going into the circuit, and then returning through the positive terminal here. Okay. Uh, Again, if I have a positive voltage, it goes out the positive terminal and returns through the negative terminal, like so. Another way of um, another way of expressing a negative voltage source is to reverse the polarity of the terminals. I can say that I have a voltage source, as in here. I can say that I have a voltage source with the positive terminal on top and the negative terminal at the bottom, and it is minus 5 volts. That is the same as saying that I have a voltage source of 5 volts with a negative terminal at the top and a positive terminal at the bottom. If I follow the convention that always the current of a positive voltage source, as I have in the first case, goes out the positive terminal and returns through the negative terminal, I can see that by reversing the polarity of the terminals between these two circuits on the right and reversing the sign of the voltage source, I have the same outcome. I still have current going this way at the bottom and returning this way to the left at the top. So in other words, the position of the polarity of the terminals has to do with the sign of the voltage being applied. If I have a negative voltage here with a positive terminal on top and a negative at the bottom, then if I make that voltage instead of negative positive, that means that I have to reverse the sign here and or reverse the terminals and have the negative terminal at the top and the positive terminal at the bottom. Now let's look at some of the quantities and the dimensions of voltage. For example, if we have the voltage that you can detect at an antenna, we're talking about microvolts. If I have a voltage to measure an EEG in the human scalp, uh, we're looking at very fractions of millivolts for an EKG to produce to measure the rhythm of the heart of a human being. We're looking at several millivolts. And then when we look at most of the things that we are familiar with, uh, like a car battery or the battery of your cell phone or the flashlight, then we're looking at single digit volts. Now, when we get into the AC outlet in large industrial uh, machinery, then you're going to look at hundreds or thousands of volts. And things like vacuum tubes and used to be used in television sets. We don't see that anymore. Used to be in the millions of volts and thousands of volts. And of course the voltage that will produce that high current in a lightning bolt is in the tens of millions of volts. And if you know how a lightning bolt is produced, you get the charge accumulated between two clouds, and the electric field between them, and the distance being so small when it's rainy and and the sky is populated by these clouds, is so high that you get this high voltage, and then of course a discharge of that energy and that charge to earth, and that's what the lightning bolt is. Now let's talk about power. So we said that we have a current, and the current is going to flow through a circuit. So we're going to get some current flowing into a load here. So we have some load here, okay? And to get that current going, we're going to have to produce some voltage, okay, here, and that's going to produce some work, so we can have that current move through that load. So we can have a negative here and a positive sign here, okay. So uh, we're going to have to do some work to move that charge, and that work is done by having a difference of potential, that voltage source from positive here to negative here. So again, let's look at the definition of voltage. It's difference in work that I have to do per unit charge so I can move it and produce that current. Uh, if I multiply the voltage times the current, I have that differential times the differential that represents the current. Remember, the current is the unit charge that I move, or that moves through a conductor through a per unit time, as the rate of change of the charge with respect to time. And then I can see that the differentials of charge cancel in each of these two derivatives. And what I'm left with is the difference in work per unit time, or the rate of change of the work that I have to do to move the current with the voltage per unit time, uh, is the power. Okay, so that's the power, and which is simply the multiplication of the voltage times the current. Now, if I wanted to know how much energy I had to put into a system, into a circuit, to move that current from time 1 to time 2, so within a period of time, if I want to know how much energy, how much work I had to do to move that charge during a period of time from T1 to T2, I'm going to call that the total energy, delta W. So what I simply have to do is integrate the power. I integrate the power um, during that period of time, and integrate the power with respect to time, and which is the same as integrating the product of the voltage and the current. This is some simplified notation, but keep in mind that these voltages and currents can be functions of time. They don't have to be constant numbers. They can be functions of time, in which case I would multiply these two functions and take the perform the integration with respect to time. Now let's look at when we calculate power. Uh, let's say that we have this circuit element over here, okay? And there is a current, flowing uh, into that element, and there is a voltage also across that element with a positive sign over here, and a negative sign over here. If I have an element with a voltage across it, and the current is going into that element through the positive sign, we say that that element is absorbing power. We say that that element is absorbing power. Okay, uh, that's the convention. That's also part of the positive sign convention. So in this case, for example, if I have um, a current that is flowing into the negative sign, okay, not the positive, but it's flowing into the negative sign, we say that this element is sourcing power. And that's why we said that voltage sources, and uh, in the previous example, they're sourcing power when the current is flowing out of the positive terminal. So here we have this current here, okay, is going into the negative sign uh, of that 2 volts and flowing out here. So basically this is looks like this is a voltage source, a 2 volt voltage source that is sourcing 4 amps into or 4 amperes into this circuit or system. Another way of drawing something like this, again playing with the sign of the quantities, is that I can say that I have a negative 2 amps or 2 amperes current flowing into the positive terminal here and coming out the negative uh, terminal. So in this case, we have to keep in mind that the current is negative. So a simple way of doing this is to change the sign of the current. So I can say that I have uh, two 2 amps here, okay, and that is flowing in the negative direction, okay. So instead of minus 2 amps going this way, I can say that I have 2 amps going this way. And if that is the case, then I have 2 amps coming out of the 2 volts supply. So still, this is a source. The rule is that when all quantities are positive, the current and the voltage, and I have the current flowing out of the positive source or the positive terminal, uh, I have a source. I have a voltage source in this case. Like it would be in this case, here, okay? If I have a positive current flowing through the positive terminal, we say that this part of the circuit is absorbing power. So here we have a source is delivering, is sourcing 2 volts, that's the voltage, times 2 amps, that's the current. So 4 watts, that's the units of power. So this part is sourcing 4 watts, and this part is absorbing the 4 watts, is absorbing that power, that energy, because the current is flowing through the positive terminal, the positive current, because we change the direction here when we change the sign. Now let's talk about some other circuit elements, specifically independent and dependent sources. We're going to take a look first at independent sources. Independent sources can be of two types: voltage or current. So what does being an independent source mean? What it means is that regardless of how much current, if you are a voltage source, regardless of how much current you need to supply to the circuit, depending on what load you have attached to you, your voltage, the voltage that you deliver is the same, it's constant. It doesn't change with the amount of current that you have to supply, that you have to source. If you are a current source, if you are, and this is the symbols for the voltage source and the current source, if you are a current source and you are a constant current source, it doesn't matter how much voltage is going to be attached to your terminal, depending on the load that you have attached to the source, you're always going to deliver the same amount of current to the circuit. So that's what being an independent source means for both voltage and current. Now, we can also have dependent sources, and this come in 4 flavors. We can have a voltage dependent voltage source, and the mu here, the mu is it's just a constant parameter, a multiplier, in which case the voltage of this voltage source is dependent on the voltage across two terminals in some other part of the system, in some other part of the circuit. So that would be a voltage dependent voltage source. We can also have a current dependent voltage source. What that means is that the voltage supplied by this source is depending on the current in some other part of the circuit. So, for example, the current flowing in this part of the circuit, and the R is simply some constant multiplier. So those are the two possible dependent voltage sources that we can have. One depends on a voltage, and the other one depends on a current, but they're both voltage sources. Then we can have dependent current sources. So here we have a voltage dependent current source where the amount of current that is supplied by this current source is dependent on a voltage somewhere else in the system, somewhere else in the circuit, and the G is a constant multiplier. And finally, we can have a current dependent current source here, in which the current that is supplied by this source is dependent on some other current in the system or the circuit. And again, beta here is a constant multiplier. So again, we can have two dependent voltage sources. One depends on a current, one depends on a voltage, and two dependent current sources. One depends on a voltage, and one depends on a current. So this is the conclusion of this submodule. And again, we looked at the SI system of units and the standard prefixes. We looked at the very basic definitions of electrical quantities, namely voltage, current. We talked about charge, and we also talked about power, being the rate of work that has to be done to produce a current with a voltage, and we looked at the total energy that we could supply to a system to do the same thing, to move an amount of charge, i.e. a current, with a voltage for a period of time. We looked at that. We looked at the definitions of independent and dependent sources. Just did that. And we looked at how to calculate power and when the power was absorbed, very important. We also calculated the power using the passive sign convention. And what this simply meant is that if we have all quantities being positive, and we have the directions and the polarities, the directions of the currents and the polarities of the voltage to account for that, if we have current that is coming out a positive terminal and going in uh, through that circuit element through the negative terminal, then we say that that circuit element is sourcing power. But if we have a current that is coming into the positive terminal of a circuit element and coming out the negative terminal of a circuit element, then we say that that circuit element is absorbing power. Okay. Normally, loads are absorbing power because they don't generate any power. Sources normally are sourcing power, but they can also, if there is some other source in the circuit that is stronger than that source, they can also absorb power. In that case, then the power is the power is positive when it's absorbed and negative when it's sourced. So we look at it from that perspective. When you source power, the power is negative, and when you absorb power, the power is positive. And this concludes this submodule 1.1 for DC analysis.